I made a simulation benchmark comparing the performance between assembly and Unity, as well as Unity dots. And the result might surprise you. Or maybe not. I don't know which you think is going to be the fastest. So keep watching so you can find out if you get surprised or not. Why compare these two quite different technologies, you ask? For views, of course. Well, not just that. Let's start with a little bit of background. A few years back, I was thinking about making a game about building roads to improve traffic. One of the main goals was to have an impressive simulation with lots of cars on the screen at the same time. So I knew I needed something that would enable me to write a really performant game. At that time I started to wonder why no one was using assembly when making games anymore, and investigated the possibility of making a 3D game with DirectX and assembly. It was actually not that hard to get going. However, I knew that it would take more time than using something like Unity. Both since it is faster to write C# than assembly, especially since I had several years of professional experience with C# and none with assembly. And Unity also comes with a lot of things that are useful for making a game. At that time, Unity Dots recently had its first preview version released, so I was thinking about if that would be a good fit for my game. In the end I went with assembly for that project, and I have a few videos about it you can watch if you are interested. Just click the icon in the top right corner. Since then, that game has been put on hold, so I can make some smaller games to try to get the sustainable income from indie game dev. But I will get back to that game at some point. And I will probably use assembly for one of my upcoming games that is going to feature a large number of entities on the screen. So now that Unity Dots has matured quite a lot since I last looked at it, it felt like a good time to compare it to assembly. If Unity Dots would straight up beat my assembly, then it would be hard to justify, even to myself, why I should not just use Unity instead, and probably speed up the development process. So in this video I will compare assembly to 6 different Unity versions. Unity Game Objects Mono, Unity Game Objects IL to CPP, Unity Data Oriented Mono, Unity Data Oriented IL to CPP, Unity Data Oriented Burst, and Unity Dots. I will go into more details on what differs between these versions later. Let's take a look at the benchmark simulation. It is called Combat Bees and is based on the sample project from a Unity Dots exercise. I'll have a link to the original project in the description. I simplified it a bit to decrease the time to create all the different versions. It consists of bees divided into 2 teams that spawns until there are 100,000 bees in total, 50,000 for each team. The bees have a simple swarming behavior, trying to stay close to other bees but not too close. And they will choose a random alive enemy bee and target it for attack, charging against it when it gets close enough and killing it. Dead bees fall to the ground and despawn after a while, freeing up space for a new bee to be spawned. I'm running this on the following hardware. Nothing special here, but I have purposefully chosen a very simple model for the bee, just 2 quads, to make sure the benchmark is not GPU bound on my computer, since CPU performance is what is interesting when comparing something like assembly versus Unity. Anything running on the GPU would most likely be pretty much the same speed in both solutions, given that the render code is good enough in both versions. Let's take a look at the code of each version so you know what the different versions mean. All the code is available in a GitHub project linked in the description, so you can check it out in more detail yourself and run it if you want. Let's start with the Game Objects version. This is a typical Unity project where each thing in the scene is a game object, which in this example means that each bee is a game object. This version is tested in 2 builds, one with Mono and one with IL to CPP. I quickly describe the difference between the 2 ways of building for anyone not familiar with C# or Unity's version of it. The Mono build just compiles the C# code to an intermediate language code, just as C# usually is compiled. Then when the app starts, it gets compiled into machine code with the just-in-time compiler as needed. Mono is an open source implementation of the .NET framework, and that is what Unity uses in these builds. The other type of build, IL to CPP, is a transpiler that converts C# IL code to C++ code, and then the C++ code gets compiled for the target platform. Usually this results in faster execution than the Mono version. Back to the Game Objects version of the benchmark. It is quite simple and it's basically made up of 3 files, a bee spawner script, a bee logic script, and a bee class for the bee data. The bee spawner is a mono behavior that spawns new bees each frame if needed by instantiating a bee prefab. It also holds some utility functions for getting an ally or enemy bee and killing a bee. The main functionality is in the bee logic script, which is attached on each bee game object. It handles the whole bee behavior in this update method. And the bee class just holds the data for bee. It has a vector 3 for position, 1 for velocity, and the third one for direction. It holds which team it belongs to as well as references to an enemy target if it has one, and a few other things. The next version is a more data-oriented version, but without using anything from Unity dots. It is still just normal Unity functionality and normal C#. This one is also built both in a mono version and an IL to CPP version. Here the architecture is quite different from the GameObjects version. There are just a few GameObjects in the scene, as the bees are just represented as data in different arrays and then rendered using instance rendering. Let's start with a look at the data. If you are used to object-oriented programming, this might look a bit unfamiliar to you. There is no bee class or struct in this version. Instead, the bee is just represented by an index. It is very much inspired by the entity component system, ECS architecture, that is used in Unity dots, but a much simpler version of it. There are no explicit components here, just some structs to bundle some of the data together and then a bunch of arrays to hold it. For example, the moment struct consists of 2 vector3 structs, and then we have 2 arrays of these, one for each team. This way we don't need to store which team a bee belongs to anywhere. That is implied by which array its data is in. Similarly, there is nothing storing if a certain bee is alive or dead. Instead, there is just 2 ints for each team holding count on how many bees are alive and how many are dead. Then I just make sure that all the alive bees are always in the first part of the arrays up until the alive count index, and then the dead bees data starts. The logic is divided into systems, each having its own run function. I show you 2 of them here, and if you are interested in seeing them all, just check out the source code on GitHub. Let's start with how new bees are spawned. It's done here in the spawn bee system, but the actual logic for spawning a new bee is hidden in the spawn bees function, so let's take a look at that. First it checks if there are any dead bees, because if there are, we need to copy those to make room for the new alive bees. Remember, the order in the arrays tells us if a bee is alive or dead. initBees is the function that actually spawns a new bee. There is no allocation needed, since all the data for the bees are statically allocated and always present during the whole runtime of the application. Spawning a new bee is then just a matter of setting the data in the different arrays for the bee index and then incrementing the alive count variable for that team. Next, let's take a look at the bee movement system. This system is responsible for updating the velocity and direction of the living bees. The actual logic is in the update movement function, which is called twice from the run function, once for each team. This function only operates on the alive bees, so it just loops through all the indices of the alive bees. Then it gets the data needed from the arrays and modifies the velocity and the direction of the bee based on the same logic as in the other version. Before making a full dots version of this, I wanted to see if just using the burst compiler for the system logic would increase the performance of the project, so I made that version. This required some changes to the data, such as switching all the arrays to native arrays, since you could not use managed objects in the burst function. Besides that, the code is pretty much the same as you can see here in the update movement function. The difference is that we need to use unsafe, so we can send the arrays as raw pointers. It was the only way I managed to send arrays to a burst function. And the syntax gets quite ugly even if I have hidden the worst under the extension method getPointer. We also lose the type safety, but hopefully it'll go faster. You'll have to wait for the results section of the video to know. Next, let's take a look at the Unity dots version. Here we divide the data into components. In practice, it is quite close to the previous versions, but instead of storing an alive count and dead count and ordering the bees, here we have components for alive and dead, as well as components for team 1 and team 2. All these components are empty, so no data needs to be stored for them. They will just function as tags for entities. Behind the scenes, I assume these will behave a bit similar to how I handled teams and alive versus dead in the previous versions, but a bit more general, and with that of course a bit more complicated. Spawning a new bee in this version is done by instantiating a new entity, as can be seen here in the bee spawn system. Then I add all the components with the starting data to that entity. Then let's look at the bee moment system. This is divided into 2 parts, one update function for the system and a job that does the logic. The update function sets up some data and then schedules the job for each team. One extra thing we need to do here compared to the previous versions is to make a copy of the moment data for each bee. For that, I just use a native array for each team that is created on startup. We need those to get data from allied bees inside the job without race conditions. Since the job is run on any of the bees in parallel, we cannot access the data for other bees inside the job without the risk of reading data that has partially been written to. So making an extra array for that data and double buffering it was the way I found to solve this in dots. It was not my preferred solution because I think it is quite unnecessary to make a copy of the whole array of position data in this case. The code picks 2 random bee indices out of 50,000 to read from for each bee, and there are only a maximum of 16 threads that can run simultaneously on my CPU, which means the risk of reading something that is currently being written to is very small. Therefore, just having a lock on the value currently being written to would be a good solution, and have a really low risk of being a bottleneck. But I could not find any way of doing something like that in Unity dots. Besides the difference in how we get the data for allied beats, the actual logic in here is almost exactly the same as in the other versions. Note that there is no moment struct in this version, since Unity has its own struct for transform related data, called local transform, which includes the position, so I opted to use that and have the velocity as a separate component. Lastly, let's take a look at the assembly version. This one, while looking very different to the other ones, is very close to a straight port of the non-dots data-oriented Unity versions. The data is structured the same, with the moment struct and the different arrays holding the data for each B. It has pretty much the exact same functions as well, I just put them all in this blogic file. Here is the update movements function. It does the same thing as that function in the other version, just on a few more lines. At the start of the function, I get the addresses of the arrays needed and store them in registers to be used later. I also set up some local variables and store them in registers. I make sure to use registers as much as possible and avoid reading or writing to memory when possible, even the stack, since a register read or write is always faster. But of course, there are only so many registers, so sometimes I need to push things on the stack. I use simd instructions to do the vector math, which means we for example can multiply two vectors together with a single instruction on the CPU. There is another difference between the assembly version and the non-dots Unity versions I just want to mention. In the assembly version, the transform matrix for the B is calculated on the GPU in the vertex shader. This means less data needs to be sent from the CPU to the GPU, and a bit less computation needs to be done as well. In the assembly version, 28 bytes per B is sent, 12 bytes for the position, 12 bytes for the rotation, and 4 bytes for the size. In the Unity version, it is 64 bytes, a 4x4 matrix of floats. This might seem a bit unfair at first, but this is a large benefit of writing custom solutions versus using a general engine, so I think it is fair. I don't know how the Unity Dots version handles this, since in that version this is all handled by the framework, but I would guess it is handled similarly to the other Unity versions. Now I will soon show you what you have all been waiting for, the performance results. But first, I just wanted to remind you to check out my game Sidestep Legends on Steam. It is great fun. Now back to the performance numbers. I ran each version 6 times, each time measuring how many frames it managed to process and render in 30 seconds. Then I calculated the average frame time of the run, and that is what we will look at. Frame time is the inverse of frames per second, and is a more intuitive way to compare different results. But to get what FPS number it represents, you can just divide 1 by the frame time. Let's take a look at the results. This graph shows the average frame time over all 6 runs for the different versions. I included lines for 30, 60 and 144 FPS to compare against. Most of the results are not surprising. The GameObjects versions are slower, IL to CPP is faster than Mono, and Burst is faster than IL to CPP. It is noteworthy that the data-oriented version built with Mono is faster than the GameObject version with IL to CPP. It is a good example that the way you solve your problem and what architecture you choose can be more important than the programming language. I think Mono versus IL to CPP is comparable to C# versus C++. Another observation is that there is a much larger difference between Mono and IL to CPP in the data-oriented version than in the GameObjects version. I think this is because the data-oriented version more optimally uses memory than the GameObjects version, so there is more to gain in increasing the execution speed in that version. While in the GameObject version, the memory latency is more dominant, so increasing the execution speed does not help that much. The Burst version did disappoint me a bit. I thought it would be able to do better. I had a look at the generated assembly of it, and there was nothing obviously bad with it that I could see. Some of it was probably a bit more complicated than needed, at least if I compare against my own assembly version, and maybe that could be improved with the use of some attributes in the C# code. Let's move to a zoomed-in version of the graph with only the fastest versions to discuss the dots and the assembly version results. The dots version did disappoint me quite a lot actually. Sure, it was the fastest of the Unity versions, but remember the dots version is multi-threaded, and the other versions are mostly single-threaded. The non-dots Unity versions actually seems to be able to fully utilize 2 threads on my CPU, which I guess is due to the renderer being decoupled from the logic code through pipelining, so the CPU can work in parallel with the GPU work. My assembly version is pretty much only utilizing a single thread fully though. With that in mind, I would expect a larger improvement in performance when introducing more threads than what the results show. The Unity Dots version is just under 2.5 times faster than the Burst version, while going from using 2 threads to 16 threads. Since the CPU is hyper-threaded, there are actually just 8 physical cores back in those threads, but still, I would at least want to see an increase closer to 4 times. Of course, adding more threads to a problem often does not scale linearly with the added threads, but in this example I would expect being quite close to that since it's so easy to parallelize. Memory bandwidth should also not play that big of a role in this example as well, since the total data actually needed to be processed on the CPU is around 5 megabytes. Each B needs 48 bytes and there are in total 100,000 Bs. Dots does add some additional data that is not needed in a more custom solution, but there's nothing I can do about that. My guess is still that it is mostly a memory bottleneck that Dots runs into that causes it to not be faster. And as a side note, during the measurements I realized that my RAM was running at 2400 MHz while it is rated at 3200 MHz, so I fixed that and redid the measurements. In the old measurements, the Unity Dots version was significantly slower than in the current measurements, which further supports the memory bottleneck hypothesis. The assembly version, on the other hand, while also getting a performance increase after the memory speed increase, it was nowhere near as big. It was around 30% for the Unity Dots and around 3% for the assembly version, probably due to the assembly version being much less reliant on RAM, due to better utilizing the CPU cache. Speaking of the assembly version, it was around 2.74 times faster than the Unity Dots version. And remember that it is only using a single thread for the CPU work, so there is much room for improvement by adding multi-threading support to it. So a big win for the assembly version in speed. Let's take a look at the resource usage for each version as well. I just used Windows Task Manager to measure these values. Starting with memory usage, we can see some interesting things. It is clear that Unity has a lot of extra stuff in memory compared to the assembly version. Remember, the actual amount of memory needed to store the data for the Bs is around 5 megabytes, so the memory above that is the overhead of the other things needed. For the assembly version, this is most likely memory needed for the actual window and some buffers that DirectX creates. Maybe the screen buffer, for example, but I'm not sure if that is needed to be in RAM. The overhead for the assembly version is around 20 megabytes or so. Not that bad, but in the Unity version, it is in the best case around 460 megabytes and in the worst case double that. Another interesting observation is that the GameObjects version and the Dots version are very close in memory size. I think that is due to the extra stuff Unity stores in memory for its entities in Dots and for the GameObjects. I just never thought it would be that much memory. If we take the difference between the GameObjects version with the lowest memory footprint and the simpler data-oriented version with the highest memory and divide it by the B count of 100,000, it ends up being almost 4,000 bytes per B. That is crazy compared to the 48 bytes that are actually needed. That seems like a good explanation why the Dots version did not stand a chance against the assembly version. That is a lot of extra data to deal with. Of course, you might not be reading all that data every frame, but still. Let's move forward to the CPU usage. For reference, fully utilizing a single thread on my CPU would result in 6.25% usage. But when testing a simple C++ app with just a while true loop, Task Manager reports around 9% CPU usage. Could be something related to how Task Manager reports CPU usage or some scheduling thing. Most of the Unity versions seem to utilize a few threads. The GameObjects version has a little bit higher usage than the data-oriented versions. That might be due to Unity being able to use more threads for the draw calls in that case, since those are not drawn with instanced rendering. Being able to run the CPU code faster also seems to enable a bit more multi-threading, looking at the mono, ILTCPP and burst builds of the data-oriented version. The Dots version almost takes up the whole CPU, so there's no issue feeding it with work to do in parallel, and in contrast the assembly version is very close to only fully using a single thread. The extra usage here is probably related to DirectX 11, which I think can do some draw work in parallel with the CPU work, which should not be much in this project since there are only a few draw calls. Next is the GPU usage. For the Unity version, it mostly scales with how fast it runs the simulation. The GameObjects versions are an exception. They are by far the slowest versions, but still have quite high GPU usage. This is most likely due to them not using instanced rendering. The assembly version has a lower GPU usage than the 3 fastest Unity versions, even though it renders much more frames per second. The only reasonable explanation for this is that I am much better at writing graphics code than the developers behind the Unity engine. Jokes aside, my guess is it comes back to general solution versus custom solution. Unity's renderer has to be able to handle many different cases, while the render code for the assembly version is written specifically to render this benchmark. Both the Unity versions and my assembly version are using DirectX 11, by the way. Lastly, let's take a look at disk space, mostly just because I knew that the assembly version would really crush the Unity version in this test. The Unity builds range from 64 MB to 91 MB, while the assembly version is only 1.35 MB. I have not made any efforts to make either the assembly version or the Unity version smaller in build size, so these results are just what you get if you don't really try. All versions could probably be made a bit smaller than they are right now, and it also doesn't really matter much in the end, since even the 91 MB in the largest Unity build will not be very relevant when making a full game, since that will be small compared to the size of the assets in the game. Still, I thought it was worth showing that something like Unity comes with a lot of extra stuff, bloat if you will, that you might not need to make your game, but can be hard or impossible to get rid of without switching tech. We have now seen that the assembly version absolutely crushes Unity in performance. But of course, performance is far from the only important thing when making a game. With that in mind, let's take a look at the ease of use and productivity of developing the different versions. Starting with the GameObject's Unity versions. This version is probably the most familiar version to people that are used to Unity. So the ease of use, if you have a long background in Unity using this architecture, will probably be very high. You get to use most things Unity has to offer to your advantage as well. Personally though, I don't like this style at all, and I don't find it easier to use than a more data-oriented approach, so I guess the ease of use will depend on your previous experience. I also question the scalability and maintainability of using GameObjects for everything. I find that dividing code that way has a way of getting out of hand and hard to get an overview as the project grows. Communication between GameObjects also often ends up being a bit of a mess. The simple data-oriented version is for me a bit of a sweet spot when it comes to ease of use and productivity. C# is fast to write, and in this version there is no boilerplate code needed, and no need to communicate between GameObjects, since you run everything from just one. You still can use most of the things Unity has to offer, and it is also possible to mix this version with the GameObjects version, in case you have some entities that need to use some GameObject features. The burst version, on the other hand, does not get a good score in this area. It was really awful to write, and all the typical nice things about C# goes out the window. The code ends up really ugly as well, due to the need of casting row pointers all the time. And speaking of row pointers, you also lose a lot of the type safety you usually have in C#. Normally, this would not be a big issue for me personally, but in the context of C# it feels really bad, since you are used to being able to rely on the type system, and here you just have to bypass it completely. It might be possible to pretty up this version a bit by refactoring the logic functions, but I don't think it will end up being that much better. Next is Unity Dots, the main star of the Unity versions. This was quite easy to write, and there was not much boilerplate code needed to get things going, which was good. However, the framework is a bit too declarative for my taste. Some people might like that, but I just think it makes it harder to get a grasp on what the code actually does, which is very important to me. I also think this might make it harder to keep track of things in a larger project, which makes me a bit worried about how well this scales. The way to get multi-threading working in Dots was nice and easy, so that is a plus. Another bad thing though, which was much related to the multi-threading, is that there are way too many things checked at runtime only. So I often ended up in cases where the code compiled just fine, but then the system would not run because of some violation that was caught in runtime. I understand that this type of validation might be hard, or in some cases impossible to do at compile time, but it would be good if most things could be caught statically when you're compiling the code. Then the final version, assembly. Personally, this is the one I enjoyed the most writing. I have really found increased joy in programming since I started to program in assembly. I understand that this will not be the experience for everyone, but I think every programmer should at least try it. At least just to get a better understanding of how code runs on the CPU. The assembly version did take me the most time to write. It is hard to compare it against all the C# versions though, since a lot of them look very similar with just some syntax changes. But I would say the time it takes to write code for your solution might matter more or less depending on what you compare it to. It is important to look at how much of the code you write actually does something useful for the problem you are trying to solve. If, for example, you are writing object-oriented code with a lot of boilerplate code, then most of the code you write will not have anything to do with the actual solution to your problem. That the boilerplate code is fast to write is not relevant, since you should not have written that code at all to begin with. But of course, if we assume you are writing actual useful code, then that will be faster in, for example, C# than assembly. On the other hand, when solving hard problems, I would say more time is probably spent thinking than actually writing code. So, how fast it is to type the solution might not always be so important. Assembly is also very simple to use. This might be surprising to anyone that has not tried it, but the low abstraction means there are really no surprises in what happens. Things do what you tell them to do and nothing else. However, it is harder to read than a high-level language. There is no going around that. This is by far the most obvious and strongest argument against assembly compared to a high-level language. I have to rely on comments quite a lot to more quickly be able to figure out what some code is doing, but reading assembly is a skill that improves over time, and I have only been using assembly for about 3 years on side projects so far. There are still also abstractions such as macros and functions, which both help a lot with readability, just as they do in a high-level language. Assembly might also be hard to scale in larger projects, but I have not made anything large enough to really find out yet. So far the largest project is my traffic sim game, which is still in an early phase. But it is not a problem in that project yet, at least. I'll have to come back to this point in a few years when I hopefully have made a larger assembly project. Another area of ease of use I want to talk about specifically is compile time. I think it is very important to be able to quickly try out a code change after you have made it. A compile time longer than a second starts becoming annoying, and if it goes up to 20 to 30 seconds, then it is long enough for me to check on something else, like Twitter, while it is working. That means that there is a bad line somewhere just over 20 seconds, where the compile time might as well have been several minutes, because a look at something like Twitter will not be just 20 seconds. The assembly project does assembling and starting in that 1 second window, so it is very pleasant to work with. Just call the build command and the app is running in an instant. With Unity it is a different story. Just hitting play in the editor without any code changes start the project inside that 1 second sweet spot time. But as soon as a code change has been made, it can take anywhere from a few seconds, which is enough to be annoying but not enough to switch to Twitter, to 15 or 20 seconds, which is dangerously close to the switch to Twitter time. The code generated in the editor is also in debug mode, unless changed to release, which means that the performance is significantly worse than the real builds are. In most projects that is probably fine, but in assembly you don't have to worry about that. You can use the same build for debugging as you do for release, since the code you write will run as you wrote it, and there is no reliance on a compiler to optimize it. When building a proper release build for the Unity projects, the build time differs greatly depending on if you use IL to CPP or mono. With mono it goes quite fast. The compile step is as fast as it is in the editor, and it is just the asset packaging that takes time, which in these projects are quite low since there are no assets. When building the IL to CPP, the build time is much higher at around 6 minutes. Not surprising since C++ is infamous for long build times, and compared to large C++ codebases this is nothing. But it does slow down things a lot if you need to test stuff where running in the editor is not applicable, such as testing performance on target hardware. As the last part of the video, I want to talk about performance by default. This was the tagline for DOTS when it was first presented. So does it hold up? I would say that it depends on what you're comparing to, since performance can be relative. If you compare it to normal Unity with game objects or even the data-oriented version I made, it does. The DOTS version was significantly faster than any of the other Unity versions in this benchmark. If we instead compare DOTS to custom solutions, I would say it does not even come close to fulfilling the performance by default promise. I really thought I would have to add multi-threading support to the assembly version for it to compete with DOTS, but the DOTS version came nowhere near the assembly version in performance. Also, this assembly version was not even that much optimized. I opted to make the simplest version that uses SIMD, due to that being easier to develop. It just uses SIMD for the vector math of the vector3 structs for the position, velocity and direction. This only uses 3 floats per CPU instruction, but there are 8 available. So I could have made a version that uses all 8 by rearranging the data to be struct of arrays instead of arrays of structs, which I think could result in a big performance boost. Maybe I'll have to make this version in a future video if I compare assembly to something faster than Unity. To summarize, Unity DOTS was the fastest Unity version, but assembly was even faster. I don't think this would be unique to assembly though. A good C or C++ version would probably be able to achieve the same or maybe even better performance than my current assembly version. Let me know in the comments if you want to see a showdown between assembly, C and C++ in a future video. So with these results, what should you use for your project? Unity does come with a lot of convenient and useful things, and can be easy to work with, as mentioned in the ease of use section. But a custom solution will probably end up faster and less resource intensive than a solution based on Unity, given that the needed skill and experience is present in the project and enough time can be dedicated to it. My takeaway from this benchmark will be to use assembly for my future projects that feature a large amount of entities. But if you want to use Unity, here are some closing thoughts about it. Avoid using game objects for driving many entities, since they will just tank performance. DOTS can be good if you are set on using Unity, but if the goal is to make a really large impressive simulation, a custom solution will very likely be better. IL to CPP is an almost free performance boost. There are only 2 downsides I know of. The first is the build time. But that is of course only going to be a problem in the cases you have to test things with a proper build. The second issue that might not be obvious is modding support. Unity games are known for being easy to mod, since most Unity games are built with Mono, and adding new functionality to Unity games with Mono is very easy due to the code being compiled in runtime. When you build a game with ILTCPP, there is no .NET runtime left, so your player won't be able to make mods with C# anymore. Instead, you would most likely have to expose a modding API as a C API, and then mods will be limited to that API. Not the biggest thing for most games, but some games might benefit greatly from modding being easy. That was all for this time. Thanks for watching to the end of the video. If you want to see more like this, make sure to subscribe to the channel and check out my games on Steam so I can keep making videos like these. Link in the description. And always remember that C# is a script language.